This is about the Corsica River estuary. It's a small trib of the Chester River. It was identified by the state of Maryland as a small watershed restoration site, and they have been messing around with the Corsica now for 7 or 8 years. One of the things that Bill and Jenny wanted me to do was to bring some take-home messages in this talk. So one of the take-home messages is that this was a collaborative study. It involved a range of people. They're listed here. I think if I was to talk about this collaboration in a nutshell, it was a combination of academics and agencies, and it worked really well. It is one of the most interesting and satisfying projects I have ever been involved with. I absolutely loved it. So you can read this faster than I can tell you what it's all about, but there are issues. We did lots of data analysis. We made some forecasts, and we learned a few things. One of the things I'm going to leave you with as a take-home message is, when you start a project like this, any project, bloody well have a conceptual model early on. In other words, to constrain the thinking, to make sure that all the players have got a piece of the action. And this is just one you've seen a lot of times. You know, the restored, the degraded estuary, nutrients are a big issue here. There are probably other issues as well. The take-home message here is that in these shallow little tributaries, getting light to the bottom is incredibly important. That's one of the things we learned in this study, getting light to the bottom. So this is more of a technical model, and what it really shows you are the things that we felt we needed to know to do an assessment of this estuary. So obviously nutrient sources, some of those were pretty easy to get, some of them were the devil's own business, some were cheap, some were expensive. Another take-home message is, in these kind of studies, if you're going to do some restoration, get in early so that you can get a baseline. Another take-home message is, for a lot of good reasons, many things in the Corsica were not measured throughout the entire year. I think we took the sort of, well, for whatever reason, the emphasis on measurement were, you know, you seagrass, goons, April till October. There are lots of things that come into these systems and happen other than in April through October. So that's a take-home message. We could have done a better job on this if we had done almost everything at an appropriate sampling frequency throughout the year. We did not. Another point here is that is this business about exchange with the next bigger system. This is a scary thing in Chesapeake Bay. It is now, there is evidence to indicate that you can clean up some systems, but you can only clean them so far because the gradient in concentration changes in the cleaned up system and the bigger unclean system, and the direction of transport changes. We know that there has been almost a decade-long progression and a change in dissolved inorganic nitrogen flux in the Patuxent. It used to go out. TN still goes out as a net flux, but DIN is coming in, and it's been progressively getting bigger. It now represents around 5% of the nitrogen budget is coming in from the bay. So this is really not good news. We did some modeling to get the transport at the mouth, so we had that constraint. There are two things at the bottom, burial and denitrification. My feeling is both of those are not hopelessly, very underappreciated as processes that are self-cleansing in estuaries. It's particularly important in shallow systems. And so we measured both of these in a variety of environments in the Corsica River. Those are the kind of process measurements that we're hurting for. We need to think about that. Rates of. Well, we have rates of nutrient inputs. That's really good. But in our current monitoring program, that's also largely where it stops. So when we measure things like oxygen, we have no insight on the underlying processes that create the concentration that we measure. So I'm a big fan of selective and insightful process measurements. Obviously, we can't measure them all. This is the Corsica. It's you know, maybe about 4 miles in length. It's a small little system. All of these little dots here indicate sampling of one sort or another. The triangle in the lower right is the wastewater treatment plant, and there have been some very big changes with that. Let's put this is another take-home point. If you can do comparative work, do it, because it strengthens, I think, any finding. So what we have here are two little simple examples of relating what we put into a system, TN load, and what's in the system. I mean, is there a relationship that makes some sense? And interestingly, for subsystems of the Chesapeake, there is a heck of a relationship between inputs and mass. These are on annual average time scales. And we can see the Corsica has modest inputs and modest masses. If we take and put the loads to the Corsica for nitrogen and phosphorus in the context of many estuarine systems, we can see that it's intermediate with both phosphorus and nitrogen loads, and that there is also, these are log scales on both of the axes of the bottom figure, that there is very considerable interannual variability. We know that for the big systems of the Chesapeake. High and low nitrogen loads vary by a factor of 2, which is huge between a drought and a flood year. And for phosphorus, it's approaching a factor of 3 between drought and flood years. So, another take-home message here is that multiple years of measurement is really, really important. So, one of the other take-home messages is, even before you start one of these restoration studies, do a budget, okay? I think, me included, I'm afraid to do budgets. I don't want to see what they say, all right? This is an input and loss budget for nitrogen for the Corsica, and a couple things just absolutely hit you between the eyes. And one is the diffuse loads. That rules this basin. The stormwater runoff is, you know, minor direct atmospheric deposition to the water, pretty small. Point sources, and that's the one successful implementation that's happened in the Corsica, is now low. If we had plotted that before the upgrade to the sewage treatment plant, it would be about equal to the stormwater runoff, okay? So still a small component, but that's what got the press, that's what got done, and apparently it works very well. And it also does not fix the Corsica River. Doesn't come close, so that's unfortunate. So this system exports less than half of what comes into it. All right, so dilution is not the solution to pollution in this case, although it's the biggest loss term. Denitrification is important, as is burial, and the inputs are about 119,000 kilograms per year, and the losses that we estimate are about 112. This, for all practical purposes, is a pretty balanced budget. So what does that tell us? Well, that tells us we probably have the big inputs and the big loss terms reasonably well understood. And that, I think, is important. It's less likely that we will fool ourselves if we have a budget that balances. If we have a budget that is far from balanced, then we know we have missed something. We've got bad data, we've got incomplete data, we are forgetting something altogether. I am old enough, unfortunately, to remember when water quality models did not include sediments. They weren't part of the picture. They weren't there. And that has evolved into quite more than a cottage industry, and far more than a cottage headache. But nevertheless, probably important, particularly in shallow systems. This is just to make the point. There is large interannual variability. The more color there is, the more algae there are in this system. So if we went there and measured things just in 2005, we would get a radically different opinion than if we measured it in 2003. So we really need to think, you know, multiple years. I one time got in an argument with Governor Schaefer, and he wasn't a great guy to argue with. He was, you know, fairly fiery. And his basic statement was, we've studied this debate to death. You know, I mean, you guys keep going out there year after year. What a waste of money. And so I grabbed him by the lapels and said, listen, Buster, if you were able to look at the economic situation of the state of Maryland once a year, maybe once every third year, how would you feel? He goes, oh, you can't do that, can't do that. I said, hey, you know, we're in the same boat. Anyway, I convinced him of nothing. Okay, so here's where we get to the central part of this little talk. We're trying to relate what we can manage, loads, to responses. And this is the first one where we felt we absolutely needed to link nitrogen or nutrient loads to some key response variable, chlorophyll in this case. And what we found was a nonlinear relationship. And for this kind of work, this isn't bad. It has an R squared of around 0.8, a little better than that, highly significant, but still a lot of scatter. And I think that if we follow the lead of limnologists, we can find some ways to scale that x-axis a little more that will lead to a tightening of this kind of a relationship. But the second thing here is that it's not linear. There is a sharp downward sweep, and the Corsica is in that. What that suggests is that we might anticipate more reduction than we would have thought we would have gotten from a linear type of response. So we may be on, it may be premature to call this a threshold, but on the other hand, why not call it a threshold? I mean, if we were able to crank loads down, we would be thinking about a fairly substantial response. Second thing, and I made this point earlier, getting light to the bottom is really important, so we went looking for a light or water clarity, something other variable, and chlorophyll was the strongest predictor of that. That will not be true in a lot of systems, but look at the chlorophyll concentrations here. We're talking lows of around maybe 10 or 12 and highs pushing 150. So we saw this, again, nonlinear relationship with chlorophyll and Secchi depth. Just look at the right-hand side of this figure. The dashed lines are along from the upper to the lower Corsica, water depth, and the depth to which 1% light gets to. Those are the open circles. So what we're saying here simply is light doesn't make it to the bottom, even in this incredibly shallow estuary. I mean, it is a turbid soup, and I think it's important to get that changed. DO varies all over the place. DNR did a great job of getting Conmon meters into this system. They were extremely helpful at looking at both longer scale, interannual to daily oxygen issues. And you can see here the yellow parts are daylights, the grays are nighttimes. You can see that strong diurnal pulse. We can calculate production and respiration, a rate measurement from these kind of data, and the rates of production and respiration in this system are unusually large. They are really very big. So here's just a quick look at the daily hours of hypoxia from, at the top, the upper, the middle, and the lower Corsica. And you can see it's most severe in the upper. It's almost always restricted to the warm period of the year. And we went looking again for that relationship between something that we can tie to the land, nutrient load chlorophyll, and then we went chlorophyll hypoxia. In this case, chlorophyll is really a variable that is the an index of labile organic matter, the kind of things that bacteria can respire pronto, as well as the algae themselves. So, reasonably quick. So, what about improvements? Well, here's a little map of the several maps of the Corsica, and the dark area basic in each of these maps is areas of no light. And if we change the Secchi depth from 0.7 meters, which is hardly crystal clear, to 1 meter, in other words, this much, okay? That much, not a lot. Then the change of 1% of light getting to the bottom goes from 41 to 93% of this estuary. That is kind of a thresholdy thing, and that's really a feature of the shape of this estuary. So again, a little improvement in Secchi depth could light up the bottom of this estuary, at least a little tiny bit. Okay, what can we do in terms of reducing nutrient loads? We ran 4 situations. The big one was the situation prior to the upgrade of the sewage treatment plant. So 130 is 130,000 kilograms per year. The number in parentheses are the grams per square meter that this estuary is being dosed. All right? The Potomac estuary has a dosing rate of around 25. The Patuxent on average is around 16 or 18. Back River, all right, which is really a green soup, is somewhere around 100, 110. And we see that Corsica was about 30. When we fixed the sewage treatment plant, it went from 29 to 26. The one that's down at 73 is a cover crop program where almost all of the agricultural land was considered. 1/3 of it went with a high grade, a high rent cover crop program. 1/3 of it went with a less effective cover crop program, and 1/3 of the agricultural lands they did nothing on. And the last bar, which reduces it even more, the ag land was considered, all of it, in a high rent cover crop program. There is also embedded in the last two installation of septic systems that are denitrifying and a 50% reduction in the nitrogen content of stormwater coming from the basin. I'll go quickly through this one. Stormwater in the Corsica can be important on a seasonal basis, and one of the nice things for, I think, management is that there's no memory in stormwater. In other words, if you get the facility built and it works, then you're not waiting for near-surface groundwater purging. The average groundwater age we estimate in the Corsica to be 17 years, and it ranges from 1 to about 110. Most of that comes from some nice studies done in German branch. We did not do explicit groundwater lifetimes in this system. So then we put together this little diagram, and what it really shows you is if you reduce the load by a certain amount, what are you likely to get? For two things. One was bottom plant habitat, and the other was a reduction in hypoxic hours. Neither of these are completely linear, which is interesting, and both of them indicate a very substantial reduction in these bad things, turbidity and hypoxia, with about a 50% reduction in load, which is within the range of the modest and severe cover crop program. So, in other words, if we did everything we could possibly do in this basin and got a 10% improvement, that's time to fold the tent and go home. Unfortunately, we're in a situation here where it seems like major but doable reductions seem to be needed. And in my opinion, major and doable reduction is the word for the whole bay. All right, so what are some of the things here? Sediments that receive light trap nutrients. They do it through SAVs, they do it through benthic algae, they also consolidate sediments. Resuspension is not so bad. So getting light to the bottom for nutrient trapping, sediment resuspension is really important. And that's what we need to do. The second thing is, this is a little bit technical, but if you can get light to the bottom, the recycling of nutrients from the sediments and the use of oxygen by the sediments changes a lot. This work was done by Jeff Cornwell. It's terrific. On the left, we have lighted sediments. On the right, we have dark sediments. And you can see in the top two panels, the oxygen consumption by the sediments roughly gets cut in half. In the bottom two panels, you can see that the ammonium flux from the sediments to the water on the right is still going on. Those little itsy-bitsy bars over there, you think, oh, they're not important, they're little bars. They're actually big numbers. It's that June is a Godzilla number. In other words, it's huge. And on the lighted sediments, we see a little ammonium sneaking out in June. The rest of the time, these sediments are using nitrogen. In other words, the phytoplankton can't get at it. So this is really, really important, getting light to the bottom. So here are the technical results. Diffuse loads are king, queen, prince. It's the whole 9 yards. If diffuse loads don't go down, nothing's going to happen. We have developed some relationships between biomass, clarity, and hypoxia, and these manageable things. So if all of this had been related to tidal height, we don't have a prayer. We can't manage that. But this is something we can, at least in practice and theory, we can manage. And we think that small improvements in water clarity would really jumpstart this system. So that's a really key thing. The take-home messages. I've already mentioned most of these. Get a model. If you don't have a model, I think you're toast. You're just sort of grabbing at things. You can make a fool of yourself. I'm pretty good at that, that's why I do models. A nutrient budget, make sure you get the big picture right, and to identify what you should have gone after. I mean, what they should have done, probably in the Corsica, but politically possibly impossible, was to take the 16 million or so they spent on the storage upgrade and put in a long time, really aggressive cover crop program. One of the reasons you don't do that is you're not likely to see a response for 5, 7, 8 years. So, you know, maybe we ought to change it and make political elected officials last for the residents' time of groundwater in the Chesapeake system. You know, then they might support this sort of stuff. Monitoring and process measurements. In other words, I think we need to be insightful. We need to know what is there. Okay, so that's monitoring, and we need to know why it's there. That's what I do. So yeah, this is a bold-faced plea for money. No, it's a recommendation that you carefully consider a suite of process studies because they will provide insight, they will constrain modeling activities, that is a help, and they are explanatory. Start early to get a baseline, do full annual periods. Multi-year is really important because there is so much difference between wet, dry, and average years. This was a team effort, and I can't emphasize that enough. And I put in here, when the going gets tough, and there was some tough goes in this thing, the smart collaborate. So we worked with people who knew a lot about stormwater. We took their advice in making these estimates. We worked with Staver and Brinsfield at the Ag Station because they know more about, they have forgotten today more about cover crops than what I know. So we took their advice. That was really an interesting thing. And I want to remind all of us that this kind of synthesis doesn't just magically happen. You know, it doesn't just, boop, there it is. We were able to convince Bruce Michaels from DNR that if he wanted to get a report like this, then we would need to have some support, and he provided that. It was terrific. And one of the interesting things was that Bruce underfunded us by a factor of 5 or 6. But we are academic types, and we have some discretion, and we get so interested in doing this. We did it anyway. And the money just sort of really helped support a person here or there to really do some serious crunching, which we would have never got to. So the synthesis part was really exciting. If anyone would like to have a copy of this report, just send me an email. I have it on a PDF, and I'll be happy to send it off to you. It's all been vetted and finalized, so the errors are all ours. So that's it.